Okay, this is number 17 on the practice exam. This you have a disk with a certain given mass. You're told the radius of the disk, and you're told that it's rolled from rest down a ramp, which is a certain distance tall. And you're asked to find the translational velocity at the end of the ramp. So let's first figure out what they're asking by translational velocity. Remember, we have two types of motion here. We have rotational motion and translational motion. Those come together when you're talking about energy. You have a rotational kinetic energy term. You have you have linear or translational kinetic energy. Remember, kinetic energy is a sum of 1/2 I omega squared, which is your rotational kinetic energy, plus 1/2 mv squared, which is your translational kinetic energy. So we're being asked to find the velocity, translational velocity of this thing at the end, not the rotational velocity. Well, this is just a conservation of energy problem. We're starting from rest. We have originally mgh, right? We have the mass of this thing times we have the weight of this thing times the height from which it starts. And then at the end, what this says is we'll call it E1. You still have that amount, right? But at the bottom of the ramp, there's no more gravitational potential energy. It's all been translated into kinetic energy. So what we have is this 1/2 I omega squared plus 1/2 mv squared term. Okay, and we're being asked to find v. Alright, so this seems like a really hard problem. It's actually not. Let's actually just unpack some stuff from our definitions, and we'll talk about it. So first thing I'm going to say is the moment of inertia of of a disk, a solid disk about its axis, because this thing will rotate about its axis, is just 1/2 mr squared. So what I'm going to do is I'm going to plug that into here. Alright, let me go to a new page. So I get that the energy total, and this is at the end of the ramp where I'm summing this up, is equal to 1/2. And then if I unpack I get 1/2 mr squared, and then I have an omega squared. Remember, this is I. Let me show you where that is. This is I right here, right? So when I unpack that, I get that this is 1/2 times I, which is 1/2 mr squared, omega squared, plus 1/2 mv squared. Okay? Well, and that's got to be equal to my original kinetic energy. So I'll put that down here, equals, not my original kinetic energy, my original total energy, which at rest is just the gravitational potential energy, mgh. Okay, so let me actually do some math here. Number one, you see there's a mass in every term. On the left side of my equation, which is here, I have a mass, and then again on the right side I have a mass. So I'm going to get rid of those. I'm going to actually do the math here. And I get 1/4 r squared omega squared plus 1/2 v squared is equal to gh now. Alright, so here's where the tricky thing comes in. If you go look on your formula sheet, or if you think back to class, go look in your chapter, what you'll find is that the translational velocity of a point on the rim of the wheel is going to be equal to r omega. Right? So this is actually what we're looking for. We're looking for the translational velocity. So if I make that substitution in, I'm going to get, let me go to a new page, I'm going to get 1/4 v squared plus 1/2 v squared is equal to I've canceled the m. It's equal to gh. And now I've got it. Right, I get v squared times, what's it going to be, 3/4 is equal to gh. V is equal to 4/3 gh square root. Just that simple.